So you might or see stress strain diagram like what we have here. So a stress strain diagram going to show our sample, any type of sample we have, either metal, PVC, composite, how it's going to react under the load. So first of all, before doing the stress strain diagram, I need to review the equation. What is stress? Stress means force divided by original cross section. What is strain? Strain is length. The difference in the length under two different conditions divided by original length going to give us a strain. And then at the end, modulus of elasticity, that one of the properties of the material, it is mechanical properties, going to be stress divided by strain. As you know, modulus of elasticity going to apply only in elastic region. We have percent elongation, means what is the final length, what is the original length, and how much the length increased. And we have area reduction, because you know that when we increase the length, we don't create any mass, right? Based on conservation of mass, mass cannot be created, cannot be destroyed, going to convert. How it's going to convert? When the length increase, the cross section going to decrease. This is why breaking happens. So we have area reduction by increasing force, and we have increasing elongation. This is why breaking happens at the end. And for area reduction, again, original minus final divided by original times 100. So those are our equations. And we talked about the instrument machine a little bit. Now we are going to run a sample here, understand our stress strain diagram, and then go over there and run the test for two different samples we have. So first of all, in first step, our sample is at original area and original length. Nothing happened. So we are here at 1. So where is number 1 for us? Number 1 is right here. Then we're going to start to apply the force. The force applies on number 2. I'm going to say number 2 here is number 2, elastic region. What does that mean, elastic region? Means if I remove that force, the sample going to come back to original length because it is elastic, it is reversible. This is the area that we would like to keep our samples. Why? Because we don't want to have any permanent deformation. This is temporary deformation. Elastic region or temporary deformation. So if we increase the force at number 3, we are going to pass a point named yield point. Yield stress is the area, the point between elastic and plastic region. This is plastic. So number 3 going to be somewhere here before the maximum. Number 3 is there. So at number 3, we enter to plastic region or permanent deformation. Means that if I remove the force here, the length won't come back to the original. Everything is permanent. The length's already changed. So how we can find the yield point here? So yield point, simply yield stress is force at this point divided by cross-section area, original cross-section area going to give it to us. But if you have a graph, we have a technique named 0.2% offset from origin. 0.2% means 0.002. We are going to scale that for 0.002. Put a mark here, then try to make a dashed line here parallel to elastic 1. Parallel to the linear line, because this part elastic has a linear line. So the dashed line parallel, continue, pass here, and at some point on a curve going to interfere with our curve. This point is yield. So 0.2% offset used on graph to measure yield or to find yield. So at 3, plastic deformation means everything is permanent. We increase the force at 4. Max happen at 4. We name that tensile strength. We are exactly at 4. Max happen. And then after the max, you will see that nothing happened to the length, and area going to start to reduce. We name that necking. This is max. This is necking at 5. And at the end, after necking, breaking going to happen at 6 and stop. We name that length final, length original. We have L for this part, L2, L3, L4, L5, and we can find a strain for each of those and write it down. But remember that if you want to draw a stress-strain diagram, this part is linear between 1 to, let's say, 0.2, somewhere here. So what we need to do is find stress and a strain here, find a stress and a strain here. Those are the point here. Look at that. This is number 2, and we have number 1. Draw a linear line. Where you're going to stop that? Do 0.2% offset, make that parallel, and make this line. Somewhere they are going to interfere. This is your yield stop, and after that, that's going to be your curve. This is go to plastic and permanent deformation. So now what we are going to do, we are going to try to find this graph with the instrument machine for 3 samples: steel, copper, and aluminum. And what we are going to say that, look at that. Modulus of elasticity is stress over strain. Stress over strain. Rise over run. Remember from math in high school, what was rise over run? Rise over run was slope. Means the slope is E. So modulus of elasticity is only for elastic region, which is linear. And we have rise over run. Okay? We will see that if this is for steel, has much bigger modulus of elasticity than aluminum. So means that if we assume this is for steel, for aluminum, going to be something like this, because E going to be smaller for aluminum respect to steel. Okay, we will see that, and then later on, when we finish with this lab, I'm going to share PDFs with you related to a stress-strain diagram for steel, aluminum, and copper, and you guys going to discuss those and drive some information for me and make the comparison between the results and tell me what's going to happen for different material on a stress-strain diagram. Thank you.